Hello students, welcome once again to Chem is Try. In this video, we want to consider the preparation of one of the most important gases as far as WASSCE Integrated Science Practical is concerned. That gas is hydrogen gas. This is the setup for the preparation of hydrogen gas. We want to learn how to label the parts of the setup. Then also talk about the things needed for this reaction to go on successfully. Let's delve into it. So, we have a setup over here. We have this instrument or apparatus. This apparatus with a very long base. It's a funnel, but it's a different kind of funnel. The normal funnel we know has a very short base. This one has a very long base. And this funnel is what we call the thistle funnel. So looking at our line, this line points towards the thistle funnel. So this part is called the thistle funnel. There is something that has been poured into the thistle funnel. Well, in the preparation of hydrogen gas, one way we achieve the preparation of this gas is by reacting a metal with a dilute acid. So the content of this thistle funnel, whatever we have poured into this thistle funnel, is our acid. Now, based on the question, you need to know what to put here. Because some questions will say hydrochloric acid, some questions will say tetraoxosulfate 6 acid. But I have not talked about any acid yet. So I'm writing the name simply as acid. Then we have this flask. If you look at the flask carefully, the base of the flask, the bottom is flat. Now there are two kinds of these flasks used for these kind of experiments. There is one with a flat base and one with a round base. The one with a flat base is called the flat-bottomed flask. And the one with the round base is called the round-bottomed flask. Since we have the one with the flat base, we are going to call it the flat-bottomed flask. Inside the flask, there are these round particles over here. Obviously, that one will refer to our metal. The metals we are going to react with our acid to produce the hydrogen gas. Now, if we produce the gas by reacting the acid with the metal, what could happen is the acid will start trying to escape. But we need the gas. We don't want the gas to escape. So we place something inside the flask so that it will prevent the gas from escaping. And that thing we put inside the flask to prevent this from occurring is what we call the cork. The cork. It is placed inside the flask to prevent the gas from escaping out of the flask. But you can see that this cork has two holes inside. One hole for the thistle funnel and the other hole for a certain tube. That certain tube is called the delivery tube. So we place our metals first inside our flat bottom flask. We cork it. And the cork we use has two holes inside. In one of the holes, we are going to fix our thistle funnel. That is the funnel with a very long base. And in one of the tubes too, we are going to fix, in one of the holes, we are going to fix our delivery tube. So that if we pour the acid through the thistle funnel into the flat bottom flask and the acid comes into contact with the metal, hydrogen gas will be produced. The gas would want to escape, but the flask has been corked, so there is no room for it to escape, except through the delivery tube, so that the gas can be collected. We try as much as we can to bring our thistle funnel down, such that when we pour the acid into the flat bottom flask, this thistle funnel will get partly immersed in the acid, so that none of the gases will be able to escape through the thistle funnel. Hydrogen gas is collected over water. This is a trough, a big container called a trough. Then there's a liquid in a trough. That liquid is water. This jar we have here is called the gas jar because it is used to collect gases. Gas jar for collecting gases. But the gas jar has been placed on a certain apparatus. And that apparatus is called the beehive shelf. Beehive shelf. It is serving as a stand for the gas jar. Please, don't ever write this one's name as the beehive stand, because it is not called the beehive stand. It is called the beehive shelf. The beehive stand is used where people rear bees for honey. The one we use in a chemistry lab is called a beehive shelf. Hydrogen gas does not dissolve in water. Therefore, the gas can be collected over water. But since the gas is very light in density, it will be collected up inside the jar. So whatever fills this empty space found at the top of the jar is our hydrogen gas. This is how hydrogen gas is prepared in the lab. I hope now you can pause the video, go back and check the labeling of the parts very well, because you need to know them. When they ask a question concerning this preparation of hydrogen gas, they will definitely ask you to label the parts. Sometimes they will write the parts as I, to whatever. Then they will ask you to identify the parts labeled I, to where they are going to end at. And I hope by now you should grasp the labeling of the parts of the setup for the preparation of hydrogen gas. Well, that was just by the way. You want to delve a bit deeper and look at questions they could ask, follow-up questions they can ask concerning this setup for the preparation of hydrogen gas. Now, the first question they could ask you is, what substances can be reacted together to produce hydrogen gas? Well, I said it earlier on that a metal would react with an acid, in fact, a dilute acid, to form a salt, then liberate or produce our hydrogen gas. But there are more to this. It is not any metal that reacts with a dilute acid to produce salt and liberate hydrogen gas. And it is not every dilute acid that can react with a metal to produce hydrogen gas. That is one of the things we want to talk about today. So let's talk about the metals. There are a lot of metals on the periodic table. In fact, if you consider the periodic table of elements, the metals are more than the non-metals and the semi-metals combined. So you can think about a lot of metals for this reaction. But the ones that are suitable are calcium, magnesium, aluminium, iron, zinc. These are the common metals we use for this experiment. There are some metals we could have used. The group 1A metals. The lithium, the sodium, the potassium, etc. Granted, when you react these metals with a dilute acid, you are going to still liberate hydrogen gas. But there is something about these metals. They are highly reactive. So reactive such that when you place lithium or sodium or potassium into a beaker containing water, they will run speedily in the water, releasing lots of hydrogen gas, and even these metals in the water self-igniting. So the metal gets itself light up on fire when it is placed in water. And sometimes even that causes an explosion that breaks the beaker and spills whatever is produced around. So if these metals in just water are behaving that violently, causing even explosion, just imagine placing them in a dilute acid. They are going to behave the same way. But this time, if the container should break as a result of the explosion, what gets spilled onto the person performing the experiment becomes an acid, which is very dangerous. Because as we already know, acids are corrosive. So because these metals react violently, even with water, we do not use them for these experiments. Although when we use them for the experiment, we are still going to get a hydrogen gas. We can't control that violent reaction. So we do not use these group 1A metals for the experiment. There are other metals too. We have copper, silver, gold, mercury, platinum. We do not use these metals either for this reaction, or because these metals are not reactive. They are dull metals, such that when you place them in an acid, they are unable to remove the hydrogen and replace it. Okay. We don't use copper, silver, gold, mercury, platinum for this reaction. We know these are metals, but they are what we call unreactive metals. They are unreactive. As such, when you place them in a solution of a dilute acid, they wouldn't be able to displace the hydrogen and form a salt liberating hydrogen gas. Don't worry. You look at the general equation for these metals in the preparation of hydrogen gas. When you look at those equations, we will look at what is happening, and we are going to get it clearly why these metals cannot produce hydrogen gas when they react with a dilute acid. That said, it's not any acid that can give us this result. We can use hydrochloric acid for this reaction. We can use tetraodosulfate 6 acid for this reaction. But we don't normally use trioxonitrate 5 for this reaction. No, because this acid would react with calcium, iron, zinc, all right, but we are not going to form hydrogen gas. In fact, the reaction that will occur is not a normal acid-metal reaction. No, it will be a redox reaction, whereby we are going to form a salt, all right, but in addition, we are going to form an oxide of nitrogen instead of hydrogen gas. So we don't normally use nitric acid for this experiment. You can use nitric acid for this experiment only if the metals you are using are magnesium and manganese. Remember them, the two M's, magnesium and manganese. For them, they will react with nitric acid, all right, to form a salt and release hydrogen gas. But if you don't want any trouble, avoid nitric acid in this reaction. If you don't want any trouble, avoid the group 1A metals in this reaction. And definitely avoid these unreactive metals. So let's look at how a reaction looks like. If we take a metal like calcium, calcium as a solid metal can react with hydrochloric acid to form calcium chloride and hydrogen gas. So the hydrochloric acid is in aqueous state, calcium chloride is in aqueous state, and the hydrogen is a gas. Also, we can have aluminium reacting with the hydrochloric acid to form aluminium chloride and release hydrogen gas. We have aluminium metal reacting with hydrochloric acid to form aluminium chloride and hydrogen gas. We also have zinc metal reacting with either HCl, but this time let's try tetraodosulfate 6 acid to form zinc sulfate and hydrogen gas. We also have magnesium metal reacting with sulfuric acid to produce magnesium sulfate and hydrogen gas. Zinc can also react with hydrochloric acid to form zinc chloride and hydrogen gas. Magnesium can also react with hydrochloric acid to form magnesium chloride and hydrogen gas. Calcium, aluminium, they can react with sulfuric acid to form calcium sulfate and aluminum sulfate respectively together with hydrogen gas. If you look at the reaction, you realize that hydrogen was already moving with chlorine in HCl. But what happened? The metal came to take the position of hydrogen, and now hydrogen is standing there alone. The same happened with aluminium meeting HCl. Hydrogen is moving with chlorine in HCl. But what happened? Aluminium came to replace hydrogen. And now hydrogen is standing there alone. Look at zinc and sulfuric acid. Zinc came to replace hydrogen. Can you see it? Then the hydrogen came to stand here alone. Magnesium came to replace this hydrogen, forming magnesium sulfate, and the hydrogen came to stand there alone. This is an example of a single replacement reaction. So in a single replacement reaction, we have a compound made up of a cation and an anion. Then we have a single substance, normally a metal, standing there alone. Then the metal goes to tell the cation to leave so that it can come and replace it. Then the cation becomes lonely. Now, that is a classical example of a single replacement reaction. It reminds me of when I was in SHS. I went to the entertainment room one day. I decided to dance with one lady. When I started dancing with the lady, a Form 3 student came. By then I was in Form 2. Then he told me to kneel down. Then the senior took the lady away to go and dance with the lady, whilst I was still alone, kneeling down. Remember, the senior came in alone to meet the lady and I. And he told me to leave and go and kneel down. Then he came to take the lady. Now that is what is happening over here. Calcium is coming alone. Hydrogen has Cl. So this is me, this is the lady, this is the senior. Then the senior comes to tell me, hey, Elvis, stand there alone. In fact, kneel down. Then the senior goes ahead to dance with the lady. Do you see what is happening? Now, that is single replacement reaction. The senior was able to do that to me because he was in Form 3, I was in Form 2. A Form 1 student can never do this to me because he is beneath me. So the reason why we don't use copper, silver, gold, mercury, platinum for this reaction is simple. These metals are beneath hydrogen in something we call the reactivity series. It is a list of elements according to how reactive those metals are. And in those arrangements, we have hydrogen gas somewhere. All the elements above hydrogen can come and replace hydrogen. So, according to that series, calcium, magnesium, aluminium, iron, zinc, lithium, sodium, potassium are all above hydrogen. So when they are alone and they meet hydrogen with any anion, they can come and replace the hydrogen so that the hydrogen will be alone. However, copper, silver, gold, mercury, platinum are beneath hydrogen. They are hydrogen's juniors. So they can never come and replace hydrogen in a single replacement reaction. It's the reason why we don't use these metals for the reaction. It's the reason why we are saying these metals are unreactive. Simply because hydrogen is even more reactive than these metals in this circle. So we don't use them for this experiment. So if you are asked to state any two substances that can react to produce hydrogen gas, you can mention any of these metals and any of these acids, and you are good to go. This is hydrogen gas. In the gas jar, you can see the hydrogen gas climbing up. The mode of collection, the gas is going up. So we call that mode of collection the upward delivery. And the upward delivery is always employed, or it always comes to play when the gas is very light. The molar mass of hydrogen gas is 2 grams per mole, making it a very light gas, not heavy at all. And when you have something heavy and something light together, what happens? The thing that is heavier goes down and the lighter one stays up. So take water and a stone, a piece of stone for example. When you put the piece of stone in the water, it will sink because the piece of stone is heavier than the water. That is the same thing occurring over here. And here we are comparing the hydrogen gas to the water. Comparing hydrogen gas to water, hydrogen gas is lighter than water. As such, in this preparation of hydrogen gas, hydrogen is collected by the upward delivery method. So that is the mode of collection of the gas, upward delivery. And the reason, it is because hydrogen gas is lighter than water. So definitely the hydrogen gas will go up. The third question they can ask you is, how do we know that the gas we have produced is hydrogen gas? The thing about gases is every gas has a way we can test to see their identity. So how do we get to know the identity of hydrogen gas? All you do is light a match. I hope you know a match. Matches. Or you can light something in the lab called a glowing splint. But since normally you don't see glowing splint in most labs, what we normally do is we light a match. Then we bring it closer to the hydrogen gas we have prepared. You see the match burning with a pop sound. A pop sound is you hear pop. That is the pop sound. And that tells you that the gas you have is hydrogen gas. And that pop sound occurs because the hydrogen reacts with oxygen in the air, which is supporting the burning process to form molecules of water. And that is what is creating that pop sound. That is how we test for the hydrogen gas. Your assignment as students would be to check the past question. The year 2022, they had this setup appearing in Integrated Science Practical. In WASI 2022, they had the same preparation of hydrogen gas, but in that paper, they didn't collect it over water. They just connected the gas to a U-tube manometer. Look at that question too, and answer the questions that are beneath it. If you get them right, kudos. You are gone. If this question should come in WASI, you have no problem solving it. We could also conduct this experiment physically in the lab for you to see. If you want us to do that, please comment in our comment section so that we would prepare a video on the practical preparation of hydrogen gas. Thank you.